Everyone. Today we'll have a look at the stack analysis of a very simple C program. So this C program consists of a simple add function which takes two arguments and returns the sum of those two arguments. Let's begin by compiling this program. We need the G flag for debugging symbols. We need the M32 flag to generate a code for a 32-bit environment so that it's just easier to analyze and understand the address space. Alright, let's start with debugging the program. And let's have a window open so that we can refer to this for the source code. Let's start by putting a few breakpoints. So the first breakpoint is for the add function. Let's put another breakpoint for the main function, and we can jump right into the code with the run. Alright, we're in the main function. Let's just have a quick look at how the frame looks like right now. So here's a brief introduction about a few registers that the CPU uses. So there are general purpose registers and special registers. So general purpose registers are EAX, EBX, ECX, EDX, and so on. And some of the special purpose registers are EIP, which stores the instruction pointer, ESP that stores the stack pointer, and EBP that stores the base pointer to the current stack frame. So in this context right now, EBP is the base address of the current stack frame. Now let us also have a quick look at how the assembly code of the main function looks like. So we see that in the source code, the main function does not have any variable declarations or anything. It just calls a simple function add. And the code corresponding to that is here. That is, first we push the arguments for any function call from right to left on top of the stack. So we start by pushing 6, then 5, and followed by that there is a call instruction. So whenever there is a call instruction, the CPU immediately takes the next instruction address and pushes this on the stack as well. And we'll see that when we look at the stack. Alright, let's just directly jump into the function and see what operations are carried out. Now if we look at the frame again, we should be able to see that the EBP has changed. So right now it is FFFFD3B8, and now the EBP is pointing to the stack frame of the current executing function, that is the add function. Now let's have a quick look at how our stack looks like. So this is how our stack looks like. Remember, these are the higher addresses and these are the lower addresses. So the value 6 is first pushed on the stack, then the value 5 is pushed on the stack, followed by which the return address is pushed. We can check that using the assembly code for add function. So after the return address, we push the EBP of the main function, so that when we return back to the main function after the call to the add, we still have the context and we know what is the base pointer of the stack frame of the main function. So we start by pushing the EBP pointer first, then we have the stack pointer value stored as the EBP value. So our stack pointer will be pointing at this address, and we'll be using this address as a reference to get access to the pushed arguments as well as the local variables that we declare here. And after this, we just move the stack pointer by 16 bytes to allow for any local variables to be pushed on the stack. After this, we see that in the source code, the first instruction in the add function is declaration of an int and initializing that to a value of 3. So we use the immediate value 3 and we push it to an address that is 4 bytes less than the EBP address. So in this stack frame, the value that is 4 bytes less than this EBP is this next address, and we push the value 3 onto this address. And now if you look at the operations, it's supposed to return the sum of the two arguments which are currently on the stack. So we first need to access A, and let's see where is A located. So A is located here with respect to EBP, that is So since these are higher addresses and these are lower addresses, we need to add 8 bytes to get access to A, and that is what we see here. We add 8 to the EBP address and we get access to that value, that is A, in this case 5, and we push that value into a register EDX. And remember that all the functions which have a return value, they will store the return value in the register called as EAX. Hence all the operations that are required to return some value, they need to be put in the EAX register. And then let's look at how do we get to 6. So plus 4, EBP plus 4 will take us to return address, plus 8 will take us to the first argument, and EBP plus 12, that is in hexadecimal C, is where we'll find the value 6, and that is where we get the value of 6 and we put that into EAX. This is a simple instruction that basically adds the value of EDX with the value of EAX and stores the registers again, so it stores the value in the register EAX again. Now let's have a look at what happens in the leave instruction and the return instruction. So basically leave instruction corresponds to these two instructions. That is, we take the stack pointer back to the EBP because we're done with the operations and we want to roll back the stack. Followed by this, there is a pop instruction. So right now your ESP, the stack pointer, was pointing at the EBP. So the next instruction says pop the value at the current stack pointer into EBP register. So you remember that we had stored the stack base pointer of the main function at this address, and since we are returning back to the main function, we need to load the EBP with the right value. So pop percentage EBP is going to pop the value that is stored at this address and put it into the EBP register and decrement the stack pointer by 4. So right now the stack pointer will be pointing to the return address. So after this leave instruction, the next instruction is ret instruction, that is return. So internally ret is nothing but pop to percentage EIP. So what it does is the stack pointer is pointing to the return address. This value is popped into the EIP so that the program counter knows where to start executing after we return from the program, from the function. And then the stack again decrements by 4. So right now the stack will be pointing to this address where 5 is stored. Now let us have a look at our main function again. So in this main function we see that after the call our CPU started executing instructions from this address, and if you recollect, our stack was still pointing here and we don't need these values anymore. So this is the lower address and these are the higher addresses. So we add 8 bytes to this and we take the stack pointer away from this stack. So this instruction accomplishes that one. And after that we see that there is just a simple return 0, and as I earlier mentioned, the return value of any function needs to be stored in the EAX register, and hence we move the immediate value 0 into EAX register, followed by which there is a leave instruction and return instruction which perform exactly the way I explained it for the add function. We are still in the stack, so we can have a look at the stack again. So I executed this instruction, int temp is equal to 3, and we should be able to see the value 3 on stack. There we go. So we have pushed the value 6, then the value 5, then there is the return address, then this is the base pointer address of the main function, this is the local variable, and this is where our stack is currently pointing to. So I hope this gives a clear understanding about how the stack works and how the calls to different functions work. Thank you.